Drawing forces on objects, the spheres experience no friction and the blocks do experience friction. We'll start with number 1, and we'll start with the easy force. The weight force is down. The weight force is down. Sorry for the bad handwriting. And this object is not falling down, it's at rest, so there has to be some other force acting on it, and that other force should be up, not whatever I just drew. But that other force is going to look like this, and it's coming from a surface, so we'll call it normal. It's the force acting perpendicular to the surface. Next we have a box. This box is at rest. We'll start with the easy force, mg. Sometimes I'll write Fg, sometimes I'll write Fw, sometimes I'll write mg because my weight force is equal to all of those. They all mean the same thing, so I use them interchangeably. Feel free to use them interchangeably or pick one and stick with it. It doesn't matter to me as long as you know that they are all equal to each other and you're able to recognize the equation. So this box is at rest. It's not falling down. What's keeping it from falling down? The tension force right there. My ups are equal to my downs. There's no grid line, so I'm just kind of eyeballing this to get the general sizes. Next, the box is at rest. And now I have 2 tension forces. I've got T1 and T2. These two should be about the same, but if you don't draw them the same, it's okay. FT1. It doesn't matter which one you call 1 or which one you call 2. It's fine. But what is not fine is if you have a really long vertical component for one of them and a really long vertical component for the other one. Because these 2 vertical components should equal our weight force. My ups should equal my downs because my box is at rest. Additionally, my lefts should equal my rights because this is in equilibrium. But of course, we don't put our components on the free body diagram. I just drew them to prove a point to you or to help you understand this. So that's all you would have there. Next up, we have a ball moving with a constant velocity. So we have our weight force. It's on a surface, a floor, a table, something. And we also have a normal force. Constant velocity means that all of the forces cancel out. My ups cancel out my downs here. There is no right or left force, and that's okay. Next up, we have a box with a constant velocity. Same thing. We'll do the easy force, weight force. Why is this box not going downwards? Because there's an upwards normal force, kind of a counteract to it. Uh-oh. We have a rightward force by a hand, and we call those the applied force. Well, that doesn't look like it's moving with a constant velocity. It looks like that applied force is unbalanced, which means we're missing something. That means there must be friction here in the opposite direction of sliding. So those 2 cancel out. My ups and downs cancel out. I'm moving at a constant velocity. Here we're being pulled by a rope. We'll do the easy one, mg. And then we have a tension force in this direction. So my upward component here, that's not the only up force. So it should not equal my weight force. Instead, I should also have a normal force, where this upward component plus this upward component of my tension force equals my weight force, because this box is not sinking into the ground and it's not floating, so they cancel each other out. I have a right force in my tension. That needs to have something opposing it. The most logical thing is that there's friction because the blocks experience friction. Next up, we're on a ramp for number 7. Weight force going down. Normal force is perpendicular to the surface, so it is not straight up. Instead, it acts in this direction, perpendicular to the surface. And let's see, are we in equilibrium here? No, we're not. But the ball is accelerating down the ramp. So we should not be in equilibrium because there's an acceleration. How much is this ball accelerating by? It's not accelerating by 10 meters per second squared. Instead, to analyze that, you could create this triangle. And what we're doing is resolving our weight force into different components. So this is my hypotenuse. My weight force is my hypotenuse. This angle would be the same as this angle. So mg cosine theta on this side, and then mg sine theta on this side. So my acceleration is going to equal mg sine theta, and my normal force is balanced by my mg cosine theta. Whenever we're on a ramp, we're just tilting our axis. So normally we have our y-axis up here and our x-axis like that. Well, when we're on a ramp, we're just, you can think about it as tilting our axis to line up with the ramp. So our y-axis is along the ramp and our x-axis is perpendicular to the ramp, if you like. Or you can just draw the triangles, which is my preference. The easy one, mg. The next easy one, normal force, normal perpendicular to the surface. Remember, this little piece here is mg sine theta. Would normally cause this thing to slide down, but it doesn't because the box experiences friction. So there's a frictional force keeping it up. There's only 3 forces acting on this box. For the ball, what did I just draw? That's not right. I know it's not right because I know gravity always goes down. Normal force is going to go like this, and we also have a tension force keeping this up because that's a string. Hopefully by now you're getting the idea of this, and I can really start powering through these pretty quickly. So I have the weight force down. I've got a surface force here, so that's a normal force. I've also got a surface force over here in that direction, perpendicular to that surface. So those 2 normal forces and that weight force, the components would cancel out, and the horizontal components cancel out, and the vertical components add together to cancel out the weight force. Next, the ball is accelerating upwards, so that means I should have a shorter downwards force. So my weight force, the easy one, should be smaller than my tension force because my net acceleration is up by twice as much as my weight. Well, the tension would be twice as much as the weight. The ball is in free fall with no air resistance. Whenever we're in free fall, the definition of free fall is the only force acting is gravity. The box falls with a constant speed through the air. Well, that's not free fall. mg. Constant speed means there has to be something opposing this. That opposing force is our drag force. Ball moving with projectile motion, as soon as the ball is launched down here, any point after that, the ball is just in free fall if there is no air resistance. So it's just mg. The ball is at the peak of projectile motion. Just because our vertical velocity is stopped does not mean we don't have horizontal velocity. It also means that our acceleration is still there. We still have a weight force. Gravity is still acting on us. We still have this downward acceleration. Friction slows the box, mg. Friction opposing sliding, and we have our weight force. The normal force. The ball accelerates horizontally at 2 times g. 2g, measure of acceleration. Your weight force. So accelerates horizontally, that means this vector needs to be really long, our tension vector, because this horizontal component should be twice as much, should lead to an acceleration of twice as much as the acceleration due to gravity. Triangular cart accelerates so the box does not slide down. Well, however this happened, we've got a weight force. We've got a normal force. And we have a frictional force opposing sliding. How do I know friction goes up? Because if there wasn't friction, what direction would the box slide? It would slide down. So there has to be a frictional force. So in this case, our frictional force opposes our weight force, and those two equal each other, cancel each other out. And we have a normal force from the triangular block to the right. So from this, we can kind of tell what direction our triangular box is going. It's going to the right because the net acceleration is to the right. The next example, we have a box. So we have a weight force. We've got a hand involved. So we've got the applied force. We've got, well, that's an A, not a G. Don't let that fool you. We also have a surface. So we have a normal force. And we have a frictional force, which cancels out our weight force. Not slide down, so our applied force equals our normal force, or normal force equals applied force. The tractor pulls a box across a rough ground at a constant velocity. The reason why it's telling me there's a rough ground, it's just telling me there's a frictional force involved. That's all. Remember those clues we talked about? That's one of them. Then we have mg. We've got our normal force. And we have this tension force. Constant velocity, so our friction equals our tension. Next up, the box does not slide as the truck comes to a stop. So the truck's acceleration is going to be backwards, which means the box would slide forward, so our friction opposes that. We'll start with the easy one, mg. We've got the normal force. And then we have the frictional force back this way. Box does not slide while the truck is accelerating backward.